So, good morning. Welcome to our next lecture in biofluid dynamics. You have hopefully realized that we have a bit of a shift in the program. I had to reshuffle the lectures because Professor Jenny cannot be here today, and so I took the lecture on cochlear mechanics to today, and this is actually one out of two lectures where we talk about the inner ear. This is an extremely cool system. It's yeah, you see here cochlear mechanics today. Then next week respiratory flows 2 by Professor Jenny, and then in 2 weeks we have the lecture on the balance sense, which will be again on the inner ear. So somehow the two lectures today and 2 weeks will be paired, and balance sense and cochlear mechanics. And this is really a cool topic. I mean, I like it obviously, and I've done quite some work on that, and I find it very fascinating. And not that many people are aware of the complexity of the fluid mechanics that is going on in it. One more thing about today. I'm actually, my schedule is also quite pressed. I have to catch a train at 12:05. So I will try to be, first of all, faster than usual. And second, I will only do a 5-minute break. So I plan to be done by 11:50. So give me a chance to catch that. Okay. So if I go too fast, well, first of all, let me know. But second, the lecture notes are uploaded, and like all the mathematical details are given there, and so you should be able to follow up on that, even if I'm a bit too fast today. But let's start now. The first hour will be mainly, let's say, a bit of physiological introduction into what the inner ear is, what the ear is, what the cochlea is doing. I think this picture should be relatively clear to all of you, at least this orange part. This is the ear, obviously. This is what is called the outer ear. Everything that is in this brownish orange color is the outer ear. That's everything you can reach with your finger, or if you stick your finger in your ear. You get all the way back, maybe not all the way back, to this structure here. This is the tympanic membrane of the eardrum, the Trommelfell, and everything behind that is painted here in this lilac, violet color. And this is called the middle ear. This is still filled with air, and there's this connection. The actually, I don't know how to pronounce it in English. Eustachische Röhre, Eustachian tube, maybe that goes to your oral cavity. So this is filled with air, and it has the 3 ossicles in it. The ossicles of the ear, 3 bones that are like a lever arm mechanism to transduce the vibrations of the eardrum. And then the blue structure in the back, this is called the inner ear, and this is fluid filled with a lymphatic fluid, a bit like water, and that's where all the cool fluid mechanics is happening that we'll be talking about. But maybe first on a high level, let's state the basic characteristic of our hearing. The hearing is happening in the final sound transduction to nerve signals is happening here in this blue structure, namely in this coiled blue structure. Typical hearing range is between 20 hertz and 20 kilohertz, so about 3 orders of magnitude, which we can hear. And of course, animals have different hearing ranges. What is also interesting and not so obvious in the first place is that the inner ear does not only host the hearing sense, it also hosts the balance sense, right? They are separated in different regions of the inner ear. So the whole inner ear is this whole thing here with this coiled structure called the cochlea, and this is where the hearing sense is sitting. It works on frequencies between 20 hertz and 20 kilohertz, and on the left side, these 3 toroidal structures, this is the balance sense. This will be the topic of a lecture in 2 weeks. And there's some separation on time scales, but we'll come back to that in 2 weeks. So why is hearing important? Well, there's some obvious things why we should have a hearing. Mostly we use it, humans, for communication. We have this conversation area, this frequency range. It's around a few hundred hertz, maybe up to 2 kilohertz or maybe 4 kilohertz. This is really what we need for conversation. And what is very typical with age, we get some hearing loss, mainly at the higher frequencies, right? But of course, there's a lot of diseases which can lead to hearing loss even earlier or even more severe than what we see here. So it's not just an age-related thing. There's also diseases. And there's a bunch of hearing aids that are developed, that are available on the market. I'm certain you know the classical hearing aids, which are essentially just sound amplifiers, right? They have a microphone. These are these behind the ear hearing aids. They have a microphone in it, and they have a lot of electronics in it and smart algorithms that amplify the sound, do not just amplify the whole broadband, but certain frequency band which are necessary. These hearing aids, they would not really need any knowledge about biofluid dynamics of the ear, but there's a bunch of more, let's say, more sophisticated, more complex hearing aids that we see here. And depending on the different let's say phenotypes of this of the hearing loss, you have different types of hearing aids. There's bone conduction hearing aids, middle ear implants, cochlear implants, and so on. And once you start working with these, and this is really an interesting technology, it's better if we have a certain understanding of what is going on in the inner ear itself, how this whole hearing process works. Let me show you a few more pictures just for motivation. These are the cochlear implants. So the stuff that you see on the right-hand side, this is what is being implanted here. I think here this is called the sound processor, which is in some sense amplifying the signal, but it's not emitting a tone by a loudspeaker that goes into the ear canal. There's actually an electrode, it's this one here, mainly this tip here, that is directly inserted in a surgical operation, inserted inside the cochlea, right? And it has these electrodes, and I think it's on the order of 25 electrodes, and they, depending on the location, they can specifically stimulate different nerve cells that are sitting here along the coil structure of the cochlea. Obviously, this device starts interfering with the fluid flow inside the cochlea. Then there's another hearing aid, and this is called a bone conduction or bone anchored hearing aid. And it actually uses a secondary pathway of sound transduction. What you probably all are aware of is the air conduct sound. So when I speak, there are sound waves in the atmosphere. They come to your ear and they go through your ear canal to the eardrum. This is air conduction. This is our primary way of hearing. But if you all close your ears, if you put a finger in your ears, you essentially stop the air conducted sound, but you still can hear a little bit, especially can hear yourself even better. And this is the bone conduction. So this is a pathway where you vibrate the skull bones, the bones in the whole skull, and that will vibrate also this coil structure, the cochlea. And through these vibrations, actually, it's not completely understood how that works, but through these vibrations, you generate a fluid flow inside the cochlea, which is very similar to classical air hearing. And especially people who have problems in this whole signal pathway in the middle ear, like people who have problems with their ossicles, they can use these hearing aids, which are actually little vibration devices that vibrate, that there's the microphone out here, takes up the sound, translates it into a mechanical vibration, and sends mechanical waves through the skull bone into the cochlea. And finally, the third example, these are so-called middle ear implants. So there You also have the sound processor somewhere out here also implanted, but there's a direct mechanical device that replaces one of the bones, mainly the third ossicle, which is the stapes bone. The stapes bone, the Steigbügel, this is the one that directly pushes onto the cochlea, and you can think of it like a piston that is pushing into the inner ear and creates a fluid flow. This can be replaced by devices like these, and there's a little electromagnetic actuator here, which starts moving these little artificial incussus, artificial stapes bones, creating a fluid flow inside the cochlea. So this just is a motivation to tell you why is it important that we understand exactly what is going on in the fluid flow in the cochlea. It's not just because it's interesting, it's also because it's important if we want to be able to design these cool hearing aids, which are of increasing importance in society. So again, a bit more on the anatomy. This picture we had before, I don't think we need to talk about it that much more. We will be solely focusing today on this blue structure today and also in 2 weeks. Except in 2 weeks we'll talk about the balance. If we go and look at this object, first of all, we need to understand it's not an object by itself, it's rather a cavity in a bone, right? You cannot take out the thing that looks like the blue thing, but you can take out the bone. And if you look at the cavity in the bone, the cavity will have that shape. Maybe you see that a bit better on this graphical representation, where we actually now look inside this cavity in the bone. See here the bony structure rounded in this yellowish color, and you see the cochlea on the right, and the three so-called semicircular canals on the left-hand side. So all of this here also with the red, with these red objects, these are the sensory structures needed for the balance sense. What we look at is this side here, and the connections to the outside are through these two holes here. They're shown here as an oval window and as a round window. So this is sort of the signal connection to the middle ear, eventually to the outside. We'll come back to that. We also need to understand that this whole structure here, this whole cavity is filled not just with one fluid, it's actually filled with two fluids. One fluid is called the endolymph, and the other one is called the perilymph. From a mechanical point of view, both behave more or less like water. They have pretty much the density of water, and they have more or less the same viscosity as water. So for everything we use, we can safely assume it's water as long as we're just in mechanics. Why are there two fluids? Well, their ion content is different. There's a difference in the potassium content, so that creates an electric potential between the two fluids, and that is required to create, or this electric potential is required for the nerve cells to fire. Okay, so this is why this is separated. We have these two fluids in there, and these two fluids are within the whole cavity separated by a membranous structure. So there's membranes, and inside the membranes you actually have the endolymph, like here in this bluish structure in semicircular canals. There's like canals in a canal, and here it's also coiled, this bluish structure, which is filled with endolymph. And between the bone wall and the membrane, we have the perilymph, or here in this cross section, it's the green part, which is filled with perilymph, and between the membrane here, we have the blue fluid, which is shown here as the endolymph. I show you just a few different views of the cochlea, right? More or less they show all the same thing, but I think it helps you to get a better understanding, to see it from different viewpoints. So this is another graphical representation of the cochlea, the whole semicircular canal part is left away. What we see again here are these holes, the round window and the oval window. And actually the oval window here now is covered by this stapes, the Steigbügel, the third ossicle. So actually, to be precise, this structure here belongs to the middle ear. This is really the interface to the middle ear. And the round window, when I call it a hole, yes, it is a hole. It's the hole that goes also to the middle ear, but it is covered by a membrane. So inside it's fluid filled, and outside it's the middle ear, it's air. Air or the bones. Okay. So if we think of a signal pathway, the main acoustic signal comes through the oval window, through the stapes bone. So as you hear me speak now, your bones, your ossicles will vibrate with the frequency, with the amplitude given by the acoustic signal. They push in the stapes like a piston into a fluid cavity, or you can think of them as channels. And so it's like a piston pushing into a cylinder, driving the fluid in this direction, or, well, because it's a vibration, it's pushing in and pulling out at the acoustic frequency. So for instance, at 1,000 hertz, the stapes moves in and out of this channel. When we follow this channel here, this upper channel, so this is a perilymph-filled channel, we see it goes up like a spiral staircase. It's like a spiral staircase. Wendeltreppe goes all the way up. Think of it as for example, the stapes is pushing into the cochlea, so fluid is pushed up the spiral staircase. And here at the top end, when you have reached the top of the spiral staircase, by the way, in humans, it's 2.5 turns. In other animals, it's more or less turns. There's a little hole in here, and through this hole, you can reach a second part. So it's like two helical structures wound into each other. You can reach the second staircase, and you go downstairs again, and you end up at the round window. Okay? So the upper staircase, the staircase that goes up, when we push in, is called the scala vestibuli. Scala vestibuli, filled with perilymph. And when we go all the way down again, it's the scala tympani, also filled with perilymph. This is all perilymphatic space. And of course, the round window has to compensate for whatever is happening at the oval window. It's mass conservation. Whenever you push fluid into the scala vestibuli at the oval window, the round window has to move out by the same amount. Otherwise, we would not conserve mass. Okay, so the round window is like the compensating structure for the oval. And the third channel, that's the one between, is this little triangle here, or here you can see it. This is the scala media. Scala media, this is where all the nerve cells are sitting. It's filled with endolymph. Okay? So the main fluid flow as we push in the piston goes through the scala vestibuli, goes up, and anti-symmetric, it comes down the scala tympani, and vice versa. If the stapes is pulled out, it comes down the scala vestibuli and goes up the scala tympani. Okay? And this fluid flow, it's a pulsating fluid flow with every moving in and moving out of the piston, with pulsation of this fluid flow in this channel. We have an interaction through the membranes with what's happening in the scala media. This then eventually generates our perception of sound. Yeah, perception of sound, afferent nerve signals that go out to the brain and are then perceived as a tone. Yeah, one more slide, one more representation, more or less showing the same thing. Here, just talking about the coiling. Humans have these 2.5 turns. It's not completely clear why 2.5, why animals like guinea pigs have 5 turns, why alligators and platypus have an unwound cochlea. It's a debate. Some dimensions for humans, if you uncoil the whole cochlea, right, you unroll it, you make like a long channel out of it, you will find a total length of 35 millimeters, okay? And the diameter of these channels is on the order of 1 millimeter. Of course, here at the base, at one of the first turns, it's a bit more than a millimeter, and at the apex, it's a bit less than a millimeter. But just if you want to get an order of magnitude idea of the size of this object, it's on the order of a millimeter times 35 millimeters in length. So this is the gross overall structure or anatomy of the whole cochlea. But I already told you, inside this triangle here, the scala media, or here, there are the sensory cells, the hair cells, which then eventually lead to nerve afferents. So let's take a closer look at it in this image. Okay, so again, top left, we have the whole cochlea, and then we see a close-up and even more of a close-up. And this structure here, and you see it's rather complex, this structure, is called the Corti organ, or the organ of Corti. And this is where we have hair cells. Hair cells are pretty cool micromechanical structures. They have little hairs on one end. You see here depicted the hair bundles. You have 3 rows. I mean, this is just a cross section, but of course it goes all the way up on the cochlea, right? So 1, 2, 3. They're called the outer hair cells, and these here are called the inner hair cells. Both types are of course hair cells. They can be stimulated by tilting these hair bundles. When you tilt the hair bundles, some ion channels open up and some, let's say, biochemical processes start kicking in. And it actually turns out to be quite complex, especially the outer hair cells. They're actually not really hearing, they are actually amplifiers. But we come to that toward the very end. For now, just you need to understand that the inner hair cell, this is the hair cell that really generates the nerve afferent, which gives the signal back to the brain. So we need to stimulate these hair bundles here to create the perception of sound. So how does that work? How do we stimulate these hair bundles? Well, you see that the whole Corti organ is a complex structure with here this thing called tectorial membrane, which sits on top of these hair cells, and at least the hair bundles of the outer hair cells are to a certain extent immersed or attached to the tectorial membrane. So if there is some relative motion between the tectorial membrane and the outer hair cells, you will get a tilting of the hair bundles. I think this is shown much better in this little animation here. I hopefully can kick off. Yeah. So you see, I have a relative motion between the tectorial membrane and this whole structure here beneath. And each time we have this motion, we have this shearing motion. Kick it off again. Yep. we get this shearing of the bundles. Huh? Mind you here, the inner hair cells are not attached to the tectorial membrane, and this is a big debate. This is anatomy which is not yet understood. Huh? I mean, you cannot read it in a textbook what this is. There's some people who believe that, oh, why is this so difficult? Okay, there's some people that believe there's this little kink here in the tectorial membrane that eventually moves them. There's other people, including me, who believe there's a fluid flow that bends them. So this is all still active research. But what is important to understand here, go on to the next image. Yep, that one here. This whole shearing motion, the primary shearing motion that we see here is caused by deflection of the whole cochlear organ. So the cochlear organ is pushed up, right, from beneath, like this arrow here is showing that. Oops, here. This arrow is showing that. So the whole cochlear organ is pushed up. And what is this here? What is this blue line? The blue line is called the basilar membrane. The basilar membrane, maybe I should go back a few slides to show that. The basilar membrane is this structure here. This is the membrane that separates the scala tympani. Scala tympani is this green structure here, the lower staircase, from the scala media. So between scala media, scala tympani, we have this basilar membrane. And if we bend this membrane, we move the cochlear organ relative, or move the hair cells relative to the tectorial membrane, and we stimulate the hair cells. Okay. Good. So we eventually need to find out how to mechanically move this membrane. And if we move the membrane, we get the shearing, and somehow, maybe by this little kink in the tectorial membrane, or maybe by fluid flow, we can get also inner hair cell stimulation. IHC is inner hair cell, OHC is outer hair cells. And as I said, it's not completely clear how they are stimulated, whether it's a fluid flow, you get something like a Couette flow when you have this relative shearing motion, or if you squeeze the whole object, there's this larger structure here called the inner sulcus. If you squeeze that, you will get a Poiseuille type flow, and both of them can actually deflect these hair cells. Maybe one more thing in terms of anatomy. Look at this picture here on the left. This is a really, really interesting picture of these hair cells. So remember that this, what you see here, is only a cross section. Okay, so actually, we go up the spiral staircase. We look at the cross section, and we see 1, 2, 3 outer hair cells and 1 inner hair cells. But if we go up, they're actually aligned. So there's 3 rows of outer hair cells and 1 row of inner hair cells. And this is now a representation that you see when you look from the top onto the cochlear organ, and first you have to remove the tectorial membrane. And this is quite difficult, it's so small stuff. But when you do this and look at from the top onto these hair cells, you see here the row of all the inner hair cells. So this is this one here, many, many inner hair cells. And you see the 3 rows of outer hair cells, 1, 2, and 3. And you see these V-shaped structures. And these V-shaped structures are actually the hair bundles. In this plot here, they look just the same from this side, but when you look at them from the top, you see that the outer hair cells have these V-shaped arrangements of the little hairs. And if you think now of this in terms of fluid mechanics, what this means is that if you have in this small gap here, right, you create a fluid flow, maybe a flow that's going from here to there, right, like this Poiseuille flow, right, there to there. That would mean you have a fluid flow from top to bottom on this presentation. So they will see the V shapes from the open side, and in a vibration will also come the other way, and they will see the V shape from the tip side. And of course, the resistance to flow is different depending on which side you come from. So this probably leads, I mean, this is a hypothesis that has not been confirmed yet, but this probably means that you have a net fluid flow. It's easier to push the fluid in this direction than to push the fluid in the opposite direction. So if you repeat that, you probably will get more fluid in than fluid out, which then creates a global mixing of the fluid. But this is all very hypothetical. This is active research, but this also shows how interesting this organ actually is if you look at it in terms of fluid mechanics. But let us come back now to anatomy and micromechanics. So we have seen that we need a motion of this membrane here, the basilar membrane, right, which is the separation between the scala tympani, which is beneath here, and the scala media, which is here. So what does this basilar membrane look like? Here's a representation again of this basilar membrane, showing again here a cross-section of the Corti organ, which is sitting on top of the membrane. It's removed here in the drawing to make it more clear. And we see that the membrane itself is a surprisingly complex mechanical structure. It's a fiber reinforced structure. It has fibers here, these dots, which are located maybe at the outer edges of this membrane, and these fibers are oriented in this direction, so perpendicular to the pathway of the spiral staircase, or if you look at it as a global coil structure, these fibers go in a radial direction. So if this is the center of the spiral staircase, these fibers go out in radial direction. And as you probably know from the theory of fiber reinforced structures, if we have stiff fibers and the relatively soft matrix into which they are embedded, the overall stiffness of the whole structure is given by the distance with which these fibers are apart, right? The farther apart the fibers are, the more bending stiffness you have, the closer they are together, the less bending stiffness you have. So there's a means for this basal membrane to control its, or let's say to change its bending stiffness. So yes, it does have a bending stiffness. So if we push it up or down, that's what we need to simulate the Corti organ, we get some reaction force, so we need some force to push. But it's also important to understand there is no in this direction here, in the direction of the spiral staircase, there's no fibers oriented in that way. So the bending stiffness in the axial direction is actually very weak, right? There's no fibers going in this direction, so you can easily bend it that way. But the bending in this direction is limited by the bending or by the displacement in these fibers. So maybe one word on the or one comment on the word membrane. We need to be a bit careful. This is called a membrane because that's what people in anatomy like to call thin objects. When you are a mechanical engineer, you probably have heard the concept of membrane in mechanics, which is different. A mechanical membrane is an object that has no bending stiffness, just tensile stiffness. This is not really the case for the basilar membrane. We do have some bending stiffness. And that bending stiffness is important because it leads to these complex resonance phenomena that we will introduce in a few minutes. And this will lead to displacements of the basilar membrane by maybe up to a few microns, but down to as little as 0.1 nanometer. This is really nothing, right? And it turns out that even such small deflections can be detected by the Corti organ. Okay? So what do we know about this basilar membrane? We just looked at the local structure. when we look at the global structure of the whole cochlea, we see that the basilar membrane looks different at the base of the cochlea from compared to the apex of the cochlea. This is an uncoiled cochlea. Usually when people do micromechanics on the cochlea, they look at it in an uncoiled way because it's easier to plot and you can have a nice coordinate system. So don't be confused. This is just an uncoiled cochlea, and at the base, the basal end as sometimes called, we find that the width of the basilar membrane, so if we look at it from the top, the width is smaller, it's more narrow, and toward the end, while the whole cochlear channels are getting more narrow, the basilar membrane itself is widening. Okay, and we know that we have these fibers in this direction. So actually the width of the basilar membrane tells us something about the overall stiffness, or maybe even about the resonance frequency of the membrane as we go from base to the apex. And I think the best way to look at this is to think of this as a xylophone. Okay, the bars, the short bars of the xylophone, they have a relatively high resonance frequency. When you hit them, there's a high tone. And when you hit the long bars, you get a low frequency tone. Right? And it's pretty much like that on the basilar membrane. Right? High frequencies resonate, or there's resonance with high frequency at the base and resonance with low frequency at the end. And because there's no fibers in this axial direction, the basilar membrane doesn't really care if this thing here vibrates. The neighbor to the left will not really notice it because there's only this soft matrix which allows for okay. So it's a good way to think of the basilar membrane as a very long xylophone, which is tuned to high frequencies at the base and low frequencies at the apex. This suggests one of the important principles of the cochlea. This is called the place principle, or the tonotopic principle, or tonotopy. It simply says that we are hearing high frequencies close to the base of the cochlea and the low frequencies close to the apex. So if you have, let's say, damage of your hair cells, if the damaged hair cells are somewhere close to the apex, you'll have a problem, or a hearing loss at low frequencies, and vice versa. If you have a damage in your hair cells at the base, you will have problems hearing high frequencies. So this is pretty much what I wanted to do for the introduction to the anatomy and, say, basic physiology of the cochlea. This is more or less what we need to know. In the second part, we'll now start to try to understand how can we exploit the different resonance frequencies of this basilar membrane to actually create, to transduce a time signal, right? If you have a sound, it's like a succession of different vibrations. It's a signal that's running in time, pressure is oscillating into something which is spatially distributed into the different frequencies. You can think of the cochlea as something like a real-time Fourier transform. You get a time signal, pressure and function of time coming in, this is what you hear, and eventually you get a frequency resolved or frequency transformed signal. You decompose the whole signal into its frequency components. So this last slide for the first hour is just showing you a summary again of all the things that we have seen now. It's quite a lot. So we have these three channels. Scala vestibuli, that's the staircase that goes up. Scala tympani, staircase that goes down. Scala vestibuli is stimulated through the oval window where the stapes is sitting. The scala tympani is connected to a round window, which is compensating for whatever the oval window is doing. In between the two is the scala media, which is filled with the endolymph, and it holds the organ of Corti. The whole, I don't think I have named it yet, the hole at the end of the staircase called the helicotrema. It's actually not so important, but just for completeness sake, I want to have it here. We have the basilar membrane, which is a really important structure. It's a structure with a graded mechanical property, stiff at the base, soft at the apex. There's a second membrane we have not named yet. It's called the Reissner's membrane. It's actually not important for what we do today. Come back to this here. Yeah. So the basilar membrane is this here with complex graded stiffness, cord organ sitting on top of it. This one here is called Reissner's membrane. It's just separating the two fluids on the top. Most likely, it has no particular mechanical role in the hearing process, just to separate fluids. Yeah. Reissner's membrane, basilar membrane, organ of with the hair cells. So it's a multi-scale organ. It's a small organ, but in itself, it's multi-scale. Good. So I think this is a good point to take a break. Yeah, I was fast. So it's 5 to 11. If we can start, continue 5 minutes from today, not from today, from now, then we'll do the second part of this lecture. Okay. Okay, welcome back. I would like to continue just a short break to continue with this with the cochlear. So we have now hopefully understood what the anatomy looks like. It's a complex anatomy, and there's so many little elements to it. But let's now talk about the actual principles of hearing. How does this hearing process work? And what are the micromechanics, microfluid mechanics involved in that? So on this slide here, you see this is taken out of the web page. The transduction pathway, it's the air conduction pathway, right? So no bone conduction. It's really a classical thing where we have sound waves coming to the ear, to the pinna or auricle, there are different names for it, and going into the external auditory canal or ear canal. And there's actually already quite a bit of sound modulation happening here. So the shaping of your ear, the shaping of the ear canal modulates the sound, prefers certain frequencies, and attenuates other frequencies. But this is, in some sense, classical acoustics and not the topic of today's lecture. Then we hit here the tympanic membrane, the eardrum, which is a soft membrane, and will just vibrate according to the incoming mechanical signal. And these vibrations are then stimulating these three bones, the malleus, incus, and the stapes bone. And you can think of them as a lever arm mechanism, which is somehow amplifying or modifying this mechanical stimulation. And how is it modifying? Well, maybe the easiest way to see what's going on is to look at the size of the size of the tympanic membrane. So there's a large surface, and if we come out with certain pressure, it's moving quite a lot. At the same time, this oval window is much smaller, and so we actually do have less motion at the higher pressure, right? So in terms of conservation of work, we have here large motion at the eardrum at little pressure, and the whole lever arm mechanism is increasing the pressure, the amplitude, but reducing the motion amplitude. Okay, so this is what this whole thing is doing. And people very often talk about an impedance matching mechanism. Why do we need impedance matching? Well, we come with sound that is airborne, sound waves, speed of sound in air about 300 meters per second, and we're going into a fluid which is like water, and water, let's say, has on the order of 1,000, maybe 1,500 meters per second. If we have a jump in speeds of sound, we usually get reflections, right? You know that. We did arterial pulse propagation, and wherever we had a jump in, let's say, the size of the canal or in the speed of sound, we had these reflections. So if this was just something without this middle ear, we would just have airborne waves hitting here, this fluid space, and probably most of it would just be reflected. None of it would go into the fluid. So this is what the middle ear is doing. There's a second thing you need to realize. What we want to generate is an active fluid flow inside the inner ear. So if we have two openings, the round window here and the oval window there, and if both of them would just be two open windows, both will feel exactly the same pressure. So there will be no reason why the flow should go in one direction or the other. So only because one is exposed to air and the other one is stimulated by this mechanical force, we have this pulsating fluid flow, pushing in, pushing out, and vice versa, pulling out and pushing in. So we get this pulsating fluid flow in this structure. And somehow this fluid flow, this pulsating fluid flow, is stimulating the basilar membrane, is stimulating it with respect to its resonance frequencies, and somehow this resonance will then create the shearing motion in the Corti organ, lead to the afferents from the inner hair cells. If you Google this, and just hypothetically, because you should not, if you Google this, you will find a lot of YouTube movies which give you completely wrong representations of what's going on. There's a huge misconception in the, let's say, in the public space of what is really going on. And I hope that I will be able to give you the right message. So how do we deal with this pulsating fluid flow? Oh, no, maybe when I said this about wrong things. So one of the misconceptions is that we have sound waves in here, right? And of course, I mean, there's sound waves passing also through the cochlea, but the sound waves, just think of it, a sound wave that is in a fluid. So just to make life simple, 1,000 meters per second speed of sound, a simulation of 1,000 hertz, that gives us a wavelength of 1 meter, okay? 1,000 hertz, 1,000 meters per second is a wavelength of 1 meter. And if you look at the size of this, the length is 35 millimeters uncoiled. So 1 meter wavelength compared to 35 millimeters, you do not even see the waves. There's no, the concept of waves here is completely irrelevant. Maybe for super high frequencies, like 20 kilohertz or so, it starts maybe becoming a bit interesting. But forget about acoustics here. This is not acoustics anymore. Acoustics is out here in the air. What we have in here is classical fluid mechanics. High frequency, but fluid mechanics. Okay, so back to this. So we want to understand the fluid dynamics, mainly of the perilymph, not so much of the endolymph. We want to understand how this resonance phenomena are going on. And finally, we'd like to understand a bit about the hair cells, how they're actually simulated and how they would react. One of the first models, or the first class of models where we spend most time on it, are so-called passive models. For now, you will see at the end why there's passive and active. For now, just take them as the models of the cochlea. The first one to come up with a model was Helmholtz in the 19th century. And he simply had the idea, well, obviously, if there's this basilar membrane with different eigenfrequencies, this is just a simple resonance phenomenon. If you simulate a whole system, a whole xylophone, a certain sound, there will be some bars of the xylophone that will resonate, will have a higher amplitude, and some will have a lower amplitude. This is a really simple and nice concept. The problem is it doesn't work, right? If you think of how resonance is working, in an ideal situation where we have zero friction, no viscous losses, no resistance, resonance works in a way that we have a very sharp resonance peak, right? If we simulate it, we have a very sharp resonance peak, and frequencies or mechanical systems which are not exactly at that frequency, they will not be simulated. This is a very sharp tuning, like it gives us a very sharp discrimination of different frequencies because we have this sharp frequency tune. At the same time, if we have no dissipation in the system, we will get a ringing, right? In the extreme case, if you hit the bar, there's no resonance, the bar will oscillate forever, or at least for a very, very long time. So this will not allow for hearing, because when I speak, the frequency is continuously changing. So you do not want to have a system without any friction. So that means the system must have friction, must have dissipation in it. What does happen to the resonance curve? When you have dissipation, it's become from a sharp resonance curve to a broad resonance curve. That means if you stimulate the system with 1,000 hertz, of course, the peak resonance will be at the basilar membrane where it's tuned at 1,000 hertz, but also the bars at the lower frequency, at a bit higher frequency, they will start oscillating. So these are two competing things, right? The sharp frequency tuning against the no ringing effects. And people looked at it carefully and they just realized this cannot be the whole story. So this whole idea of Helmholtz was rapidly discarded. And it took quite some time, and there was a guy called Georg von Békésy or Békésy. He actually received the Nobel Prize, I think, 1910 for his discoveries. And one of the main things that he understood, first described, was that there are so-called traveling waves in the cochlea. Mainly, he said there were traveling waves on the basilar membrane, but we'll see later on there's also traveling waves in fluid. So what is a traveling wave? Well, obviously, it's a wave that has a direction that is moving. It's actually moving from the base of the cochlea toward the apex. So it's something that looks like what we see here. So if you think of your one single point on the basilar membrane, that single point, for that one, it just looks like an oscillation, going up and down, up and down. But the phase shift of your neighbors left and right are arranged in a way that we have a traveling wave from left to right. We have a wave speed, which is, this was Békésy's observation, which was always positive. He also observed that this traveling wave, which always travels from base toward the apex, doesn't have a constant amplitude, but that this wave has a certain peak. Slowly rising usually, and then rapidly decreasing, and usually at the apex of the cochlea, there's zero oscillation. So there must be a mechanism which somehow creates this traveling wave phenomenon, this wave propagation inside the cochlea, and which stimulates or modulates, not stimulates, modulates the amplitude such that we have a peak at a certain location. That peak, of course, is again the resonance phenomenon. So Békésy actually created this model. It's a simple two-box model, a two-channel model of the cochlea. So it's important to understand that this model neglects the scala media. So somehow it says the vestibular canal, the scala vestibuli, and the scala media are treated like one mechanical structure, because there's only like this Reisner's membrane in between, which is usually neglected. So we have a top chamber, scala vestibuli, and we have a bottom chamber, scala tympani. At the end, they have a hole for the helicotrema, and in between, we have a soft membrane, which is wide at the apex and narrow at the base to have high resonance frequencies here and low resonance frequencies here. So this is like a simplified basic model of the perilymphatic fluid flow inside the cochlea. Yeah, and here of course we have the stimulator at the oval window and its counterpart, its antisymmetric counterpart at the random. And if this system has this high level of symmetry, think of a piston pushing in here, pushing into the oval window, of course creates a direct fluid flow going toward the apex. And because if we really idealize and make this perfectly symmetric, it's easy to see that whatever is happening on the lower half on the scarlet symphony is just anti-symmetric. It's symmetric, but the opposite sign. Huh? If something flows in on the top, the same thing will happen at the bottom, which just go the other direction. So we have this anti-symmetric configuration. The first model that was really meaningful and was allowing to explain what's going on is the so-called transmission line model. It actually comes from electronics. You'll find it there, but it applies also to the cochlea. For those of you who want to read a bit more about this, there's a seminal paper by Peterson and Bogert from 1950 who wrote this dynamical theory of the cochlea. They actually, they were quite open-minded. They allowed for fluid compressibility, allowing for acoustic waves. And actually, one of the main results of their theory is that they showed acoustics can be neglected. It's really, the flow can be considered inviscid. It's an assumption, we'll come back to that, and incompressible. So they neglect acoustic waves. And to make life simple, they assumed a 1D axial flow. They say we just have a 1D flow, just either going upstream or downstream. Yeah, scalar tympani is anti-symmetric. It just solely when it is going to the apex, and scalar vestibulum must go the other way in the scalar tympani. Scalar media, scalar media is neglected for simplification. And now this is an important concept. The whole basilar membrane is modeled as a set of independent oscillators. So it helps again to think of the xylophone, right? Even though the basilar membrane is a continuous structure, we now in this model consider like a xylophone with independent bars of different lengths. And each bar is like an oscillator. When this bar is oscillating, the bar to its left doesn't know anything about this, it just doesn't care, right? So there's no connection, no mechanical connection between the different bars of the xylophone. Of course, there's a connection via the fluid surrounding it. Okay, so each bar of the xylophone is modeled by a mass, a spring, and some damping. Okay, so the only damping we have in the system comes from the mechanical damping of the membrane of each bar of the xylophone. It does not come from the fluid. It's an assumption. So if we take these assumptions, we can start formulating a mathematical model. And what I'm showing you here is a schematic representation of the scalar media. So imagine like here to the left, there would be the oval window, and here to the right, there would be the apex of the cochlea with the helica prima. And whatever is beneath here would be the scalar tympani, which is the same but opposite side. In between, I have shown here, drawn here, the basilar membrane, which is flexible. It can move up and down. I indicated here like this wavy shape. We have a certain cross section. We have a control volume dz. We have an axial direction z. So it's like what we usually do when we have a pipe flow. We have the z direction as the main axis. In the control volume, we have fluid flow coming in from the left at a certain pressure. and fluid flow moving out to the right of the control volume. So this is our control volume here, cross section A. Right. What is new now is we also have the bottom wall, which can be moving, right? And the displacement of the basal membrane, we call it eta. Eta is just the displacement, which is of course also a function of the Z coordinate. I think it should be clear that when the basilar membrane is moving up, we're making the control volume smaller, so more fluid must go out than is coming in, and vice versa. So we can formulate a mass balance for this control volume. Let's look at the different terms. We have the incoming flow WZ, so this is the velocity at the location Z, times A, times the cross-sectional area A. This is coming in, and the second term is the fluid flow that's moving out. That's W at the location Z plus dZ times A. This is what moves out. And the new term is this one here. It's eta dot. So eta dot, eta is the displacement, so eta dot is the velocity with which the basal membrane is moving. dZ here is the length of the control volume, and B is the width of the basal membrane. Okay, this is our mass balance, and we do the typical things. We divide by dZ and by A, and we end up with this term here, which ends up in a derivative dw dz or minus dw dz, and this term here, which holds the velocity of the basilar membrane. So in shorthand notation, we can write this equation like that. W prime standing for d dz, for spatial derivative is equal to d. D is now this geometrical parameter b divided by a. It's just geometry, and times eta dot, the velocity of the membrane. So we have connected the change in the velocity in the scala vestibuli to the local velocity of the basilar membrane. This is mass conservation. We need a second, well, actually we need two more equations. We need a momentum balance. For momentum balance, we have our Navier-Stokes equation, or at least a 1D representation of that, with the rho dw dt, it's the unsteady term, and here we have the nonlinear term of the Navier-Stokes equation. We have the pressure gradient, and we have the viscous term. What do we do with it? Well, first of all, we neglect this term, which is a quite a bold assumption. It's called the long wavelength assumption. This is a simplification that many people are doing because it makes life easy when you drop this term. You can argue that if the wavelength is long, it's okay to do that. We'll see later on that this assumption is actually not satisfied. But still, it works, and the results look okay. The long wavelength is the assumption, and the second assumption we made is this one here. We assume the inviscid flow, and also we see later on this may be not such a good idea. But hey, it's a simple model, and it will give us some insight. So we end up with just the first term on the left-hand side and the first term on the right-hand side. So rho w dot standing for d dt minus p prime, minus dp dz. We need one more equation, and that is actually the equation describing the mechanics of the membrane. I told you we think of the membrane as a set of bars of xylophone, each with its own resonance frequency, each with its own mass times acceleration. This is a damping term with the damping coefficient R, and the stiffness of the membrane. That is the classical oscillator equation. And now the question is, what is driving these bars? What makes them move up and down? Well, what makes them move up and down is the pressure difference across the basilar membrane. So we have a pressure up here, pressure P here, and because we're in an anti-symmetric configuration beneath, if we have a pressure plus P here, we will have a pressure minus P at the bottom, right? Antisymmetric. So what is the pressure difference? It's 2P, plus P and minus P here. So it feels the pressure 2P, or actually minus 2P. If there's a positive pressure here, a plus P, and here's a minus P, that means it will be pushed down. So that's why we have a minus 2P. So this is the representation of the membrane mechanics. And mind you that the stiffness parameter here, the K, is changing. At the base, the K is a function of Z. At the base, we have a very stiff, high stiffness, a very stiff oscillator. And at the apex, we have a relatively soft oscillator. Typically, people are using this exponential ansatz that we have for small z, the base, we have a high stiffness, and toward the apex, we have a relatively low stiffness. Okay. Let me summarize what we did. We have three equations now. The conservation of mass, which is connecting the velocity gradient, the change in velocity, to the velocity of the basal membrane, with a momentum conservation equation, which is relating the change in velocity and time to the pressure gradient, and finally we have this mechanical representation. We have three equations. Three unknowns, three equations and three unknowns, W, eta, and P. So we're safe. This is a closed set of equations. These are linear equations. They're not so easy because the coefficient K here is changing. It's not a constant coefficient. So the way this is typically solved, this set of equations, is by doing a Fourier transform in time. So you assume that the whole system is oscillating at a certain frequency omega, and you transform in time. So time derivatives can be replaced by I omega times the amplitude. This is just a tool of solving partial differential equations if we make this Fourier transform representation. Okay. So wherever we have a spatial derivative, it remains a spatial derivative. So W hat are the Fourier coefficients, which are also a function of Z, but no longer a function of time. And the eta becomes the Fourier coefficient zeta hat times I omega. So this is like the time derivative. And here we have the same for conservation momentum. We have the rho W, and it gives us an I omega rho W hat. W hat being, again, the Fourier coefficients. For the pressure, it remains the same. And for the basal membrane, this is where we have the biggest change. We can have the second derivative. This is a minus an I omega squared. I omega squared is I squared, which is minus 1 omega squared is omega squared. Okay, so we have a minus omega squared m. From this here, we get an I omega times R, I omega times R. Here we simply stay with the K, okay? So this is a way of rewriting the dynamics of the basal membrane in terms of the Fourier coefficients. And because this is now a coefficient here, coefficient in function of omega, of the frequency omega, and of the different parameters, we can also always write this as a single coefficient. It's a complex valued coefficient, which we call Z. This is what other people may call the impedance. So this is the mechanical impedance of the basilar membrane, Z, which is a function of frequency, so it has different impedances depending on frequency, times the amplitude, the amplitude of the Fourier coefficient minus 2p. Okay, so we have rewritten this partial differential equation in a free space in time, which eliminates derivatives with respect to time, and we just end up with derivatives with respect to space. So it's now a system of ordinary differential equations. Let's go to the next slide. Here we have these equations again. It's just a copy from the previous slide. And you can now start manipulating these equations to get rid of two of the unknowns. The first thing you do is you combine the conservation of mass equation and the equation for the basal membrane mechanics to replace the eta. So you know eta is equal to minus 2p divided by z, and so you can replace this eta here by minus 2p divided by z. So this gives you this equation. So we have eliminated the eta, and you can manipulate now the conservation of momentum, and you will finally end up with this equation. Now let's take a look at what this equation really is. This is now an ordinary differential equation, only for the pressure. We have a second derivative in space of the pressure, plus this term here, which has a coefficient in front. The coefficient is complex valued, and it's a function of omega and of z, of course, but it's for a given omega, for a given frequency, and for a given position z, it's a constant coefficient. So this equation can actually be solved on a computer. It's not so difficult to do that, but it's actually useful if we look at this a bit longer and try to see what it actually is. So we have a second derivative in space. What is this actually? Well, we are in Fourier space in time, right? We eliminate the time by going to Fourier transform. But here is this omega square in it, or a minus omega square. That's the second derivative in time. Maybe let's go to the next slide here. This is the same equation. I just rearranged the terms here, right? This is what it looks like originally, and it just pulled some of the coefficients to this term, such that on the second term, we just have a minus I omega squared. Okay? Just another simple manipulation. So what is this now? Okay? Second derivative in space minus, and now we know this is actually the Fourier way of writing a second derivative in time. So that's a wave equation, right? dp dz squared minus something dp dt squared. So we have derived a wave equation. And we know that the coefficient standing here is actually wave speed, or the wave speed squared, right? We have a wave speed c, which is square root of this coefficient. And at the end, this should not surprise us that much, because let's go back to what we have actually done. We have actually somehow reproduced, with some modifications, but we have reproduced what we did in the lecture on pulse propagation, right? Pulse propagation, we had a very similar way of looking at this, except we did not call this basilar membrane. It was just a blood vessel that was distending. And for the blood vessel, we had a simple relation with the distensibility. We didn't have the graded stiffness. So when we did it for the pulse propagation, we did not have this, let's say, complex behavior of the vessel wall. But other than that, we did pretty much the same thing. So we somehow re-derived the pulse propagation, except now that the wave speed is no longer a constant, which may be changing as impedance changes. The wave speed is now a rather complex quantity which holds here this impedance of the membrane. And it's even a complex valued wave speed, which is kind of a weird concept, right? what is happening to this wave speed? Well, there will be places where this wave speed will be high, and we'll actually see in a few minutes that the wave speed is high, especially here at the base of the cochlea, and the wave speed will decrease. It will get slower and slower. And as the waves get slower and slower, they will start piling up. They will start piling up, thereby increasing the amplitude. And the location where they pile up, this is the place where we have the most stimulation of our hair cells. Where do they pile up? Well, they pile up wherever the wave speed becomes zero. Is there a place where the wave speed becomes zero? Well, not quite. Huh? Why? Well, because the Z is a complex valued function, right? We have, where does the complex value come from? The complex value in Z comes here from the damping. But let's just to get the right idea, let's just forget about the damping, or let's just assume we have zero damping. Then the Z is simply here the minus omega squared plus K. So we can find a location where this impedance Z is zero. Where is it zero? It's zero wherever omega squared is equal to m over k. K over m. Or omega equals square root of k over m. Maybe you have seen this before. This is the resonance frequency of an oscillator. Okay. So what does that mean? Whenever we hit the local resonance frequency of the basal membrane, of the bar, of that very bar, the wave speed goes towards zero. It doesn't ever become exactly zero because we have this damping term, but it becomes nearly zero. So there is, for every frequency, one particular location, and this location is called the characteristic place, where the wave speed goes almost zero, except for the resonance, for the damping term. And this is the characteristic place. This is where the whole wave is piling. I'll show you some graphical representations of that in a second. There's another way of understanding that, and I don't want to go into any detail. You can read that up in the lecture notes. This is not going via the Fourier method. This is really staying in real space. And we will see with the resolvent method that wherever the resolvent, this is a mathematical concept, wherever the resolvent has a singularity, you get the resonance peak. But what this ends up with is these results. So this is essentially, or it is a numerical solution of this equation. Sorry, this one. Huh? This is a solution of this equation for a high frequency simulation and for a low frequency simulation. Let's look at this one first. So this is the base here, right? Here we have the simulation through the oval window, and we do see these traveling waves. And especially at the beginning, the waves are traveling fast. So we have a high wave speed, gives us a long wavelength. And here toward this place, the wave speed is reducing more. The wavelength becomes shorter and shorter and shorter, and the waves are piling up with an increased amplitude. And this is the place where the hair cells are stimulated the most, or the corti organ is stimulated the most. And if we reduce the frequency, we still get traveling waves, which are going really fast here at the base, but are slowing down. But the place where the wave speed goes towards zero, apart from the damping, is further down. Huh? So this is the tonotopy principle, the place principle. We have stimulation here, high frequency, low frequency. There. This is the transmission line model, and I told you there's a few things that are problematic. One of them is, maybe you remember, this long wavelength assumption. Well, I would agree here, these wavelengths are long, so it's a good assumption. But I just showed you the wavelengths go towards zero here, so it's kind of a contradiction, right? You cannot assume I have no long wavelength or no short wavelength. At the same time, the result shows you that the wavelengths go to zero. So this is a contradiction, and people didn't like that. So there were two people, Lesser and Berkeley, in 1972, who extended the model. They went into a potential flow solution. They also said it cannot be just a 1D flow, because when we have these oscillations of the basilar membrane, obviously there must be also a transversal component of the fluid flow. So they in some sense extended the model to a 2D flow field. They still assumed inviscid flow. So this allowed them to use a potential flow theory. This is what the equations look like. We still have the basilar membrane equation looking the same. Conservation momentum is now written with the fluid potential phi. Other than that, it looks almost the same as before. We do have this new equation, fluid structure coupling. D phi dy, what is this? Phi is the fluid potential. D phi dy is the v velocity, is the transversal velocity. So what does this equation say? The v velocity at the location y0, so the v velocity here along the basilar membrane, the vertical, the transversal velocity along the membrane must be the same as the velocity of the membrane itself. This is how you create the coupling between a mechanical structure and the fluid flow. This is the mathematical way of doing it. Yeah, then finally you have the potential flow equation, Laplace phi must be zero. And you can also solve these equations, and what comes out is actually almost the same as what we had before. Of course, arguably, this is, from the point of view of physics, a much better representation, because they didn't make these assumptions like the long wavelength assumption allowed for 2D flow. But at the end, you still get these traveling waves which are piling up and reaching a peak amplitude at the resonance point at the characteristic place. Here they show again like the envelopes of these traveling waves for different frequencies. Here's a very low frequency stimulation which peaks close to 35 millimeters. Higher frequency traveling waves are peaking earlier at lower frequencies. We have actually done a MATLAB model solving exactly these equations, and I'd like to show you these representations. What you see here on the bottom chart, the red line, this is actually the basilar membrane. You see how waves are traveling through. On the top, you see the flow field. This is a two-dimensional flow field of the scala vestibuli. And scala tympani is not shown, it's just anti-symmetry. Why are we not showing them in the same plot? Well, because the basilar membrane motion is a few orders of magnitude smaller than what the fluid system is doing. So they need different scales. So we put them on two different plots. Let's see what's happening when we turn on this animation. This is a simulation at 1,000 hertz, starting from a zero condition. And you see now that very rapidly, and this was starting really from zero initial flow, this is the suddenly turn on signal. We get very rapidly, we get these this steady state solution with a peaking wave here at this location, which is representative of 1,000. This is where the outer hair cells or the inner hair cells are sitting, that the brain can connect to 1,000. Okay, let's kick it off again. You see in the beginning we have a bit of a transient here. This is due to this sudden start of the signal. And maybe you can appreciate what's going on here. You see maybe the little arrows, right? Pointer again. You can stop it. No, okay. But you'll see it again here. This is second animation, just at a lower frequency. And try to see what the arrows are doing here in the flow field. Try to pick one arrow and watch what it's doing. Close to the characteristic place. Sometimes it's going up, sometimes it's going to the left, sometimes it's going down. For each fluid particle, what the fluid particle sitting there, the molecule, the perilymph molecule sees there, it's just turning in circles. Locally, it's like going in circles. The whole wave motion we only see from far away. Locally, what the molecules see is a circular motion. And of course, the peak is now close to the apex because we're at the 100 hertz here. Okay, so I showed you now a 2D extension. Now let's ask the question whether implicit assumption is a good idea. And I tell you it's not a good idea. Why? Well, we're at the very high frequency fluid flow. And we know from the Womersley theory that we're going to get boundary layers which will be super thin. Right? We see this here in this representation. Is the plot out of the lecture notes. And this is actually the Womersley number you have in the cochlea for, say that, yeah, for 20 kilohertz. This is 20 kilohertz, this is 20 hertz. And definitely we have high gradients here and even higher gradients here at the cochlear wall. This will create a lot of resistance. So assuming implicit flow is not a good idea. So we actually went on and wrote a model which solves the full Navier-Stokes equations, including viscosity. And this what comes out. So you still have traveling waves. And the overall representation on the basal membrane looks more or less the same qualitatively. Of course, you have relatively thin boundary layer effects here. You can see them here and here. But what you also find is that this whole dissipation that you have in the fluid is actually what you need to get a physiological meaningful representation, that we can actually skip the damping term in the basal membrane. All the dissipation is now coming from the fluid in the right quantity. And we can go on and look at what little molecules are doing, or little fluid particles are doing, and I told you they're going in circles. Well, are they really going in circles? Not exactly. Why? Because, I mean, these circles are super small, right? But the overall velocity field is graded. So the velocities are a bit smaller up here and close to the membrane, they're higher. So on their circular pathways, they come into different regions of the fluid flow, which means that when they come back to the beginning of the circle, they will not end up at exactly the same location. This is a phenomenon that's well known in ocean waves. It's called the Stokes drift. You have exactly the same situation in deep ocean waves. And there's a net fluid transport in the ocean with waves, even though locally it just looks like they're going in circles, but the circles are not exactly close. They're actually moving. So we do have a phenomenon that's known as acoustic streaming in the cochlea. It was already observed by von Bekeshi in 1910, but he didn't know what to do with it. And it can be explained now based on this, and you can show that you can reach velocities, streaming velocities, which are maybe not super high, but for other reason. You can wonder if they can be used for instance, for drug transporters. So time is almost over. Let me come to the very last thing, and I don't want to go any detail on that, but I want to have it mentioned. All that we have done so far are so-called passive models of the cochlea. And I promise you I would explain to you why they're called passive. Passive because there's also active models. And people start realizing, they had all these models that I showed you before, and they start realizing that these envelopes of the traveling waves, they still do not explain this frequency tuning, this way of being able to discriminate frequencies. For this, the peak was just not sharp enough. And they realized that the peak should be much more like that, and that there's an active mechanism active, something working by itself inside the cochlea, which amplifies the whole thing and creates a sharper frequency tuning. And people realized that when they found out that there's this thing called autoacoustic emission. So you may not be aware, but your ear cannot just hear sound, it can also produce sound. And this is actually used for diagnosis of ears in infants, right? Because you cannot ask them, do you hear it, yes or no? So what they do is they stimulate the ears by certain, I think, usually clicks, and a working ear should respond to a click by a certain different type of click. Okay, so there are these autoacoustic emissions. Cochlea is able to emit acoustic waves. They are triggered. Sometimes they also come spontaneously. There's also this phenomenon is also known in music. People are talking of Rameau's fundamental bass tone. So you can stimulate the cochlea by a sequence of frequencies, like 3 frequencies. In that case, 1000 hertz, 1250, and 1500. And you can find, if you consider these active processes, that the basal membrane is also stimulated at much lower frequency, much further up the apex, which corresponds to lower tones. So there's some kind of something going on inside the cochlea, which these are the 3 tones which you stimulate, and this is what the basal membrane does by itself, the active process. So the solution was in these outer hair cells. These outer hair cells, they are actually amplifiers. Once you tilt the bundles, they kick back, right? So you stimulate by tilting the bundles, and they will amplify the signal. These are really amplifier modules here. Turn on again, if it works. So amplifiers. So this is really a relatively complex processes here. But for us, it's sufficient to understand that we amplify. If we stimulate at the 40 hertz, the outer hair cells will amplify the signal by 2 orders of magnitude. That's 40 hertz. And they're actually cool amplifiers because they only amplify the lower stimulation amplitudes. And if we have stimulation amplitudes of 100 decibel, which is already quite loud, they stop amplifying. Yeah? So they help us hear sounds at low frequencies. There's people who try to model that and try to model the physiology of these outer hair cells, came up with quite complex models. You can try to represent this by adding additional oscillator elements. We did this in our model, and we use this additional equation, which is a nonlinear oscillator equation. And what it actually turns out is that if you add this to it, you allow for these additional nonlinear processes. You can simulate now, in that case here, with a frequency of 12 kilohertz, 10 kilohertz, and 8 kilohertz. And without these active outer hair cells, you just get simulation at these frequencies at the base of the cochlea. And if you turn on the active outer hair cells, you get these nonlinear mechanisms going on. And you also get subharmonic simulations at lower frequencies, which could explain some of the phenomena like Rameau's bass, or things that are known here as the frequency tuning, the local amplification, compressive nonlinearity, and distortion. That's all. That's all, and I'm actually 4 minutes longer than I wanted to be, so I have to close here. Thank you, and I'll see you in 2 weeks next week as Professor Yin. Okay, goodbye.